Introduction. My name is Sungbin Lee. I am a junior undergraduate student at the Department of Physics and Astronomy in Seoul National University. Today, I would like to present about quantum computation advantage using photons, Gaussian boson sampling. So I'm right now in Chicago in the United States right now. It's 5 a.m. in Chicago. So I'll be very quick because I have to go back to sleep. And so this presentation will be, I will like maybe 20 minutes or even less. So I will give a brief introduction of what Gaussian boson sampling is, why it is important, and how to perform Gaussian boson sampling with experimental purposes. So these two figures are taken from this science paper published in 2020. It was cited, I guess, more than 3,000 times by now, one of the most cited papers in the 2020s. So these are the actual experimental setups that this author have used to perform these experiments. It was performed by Professor Janwei Pan's group in the in USTC, the University of Science and Technology of China. And what they basically did is to generate 50 squid state modes and insert it back to a 100 by 100 unitary matrix interferometer, which is given by optical interferometers as given by these setups, and measure the outcome single photon states with these detectors on the edges. So I'll explain briefly about what that exactly is. So if you have listened to my presentations for quite a while, I guess you have already seen some of similar papers here. What basically it means that Gaussian boson sampling is quite similar to random circuit sampling. Actually, it's mathematically identical, only experimentally there are some differences. So they're both designed to be easy for quantum computers, but hard for classical computers, because actually that's what quantum supremacy is all about. But boson sampling measures the output states in a photon basis number. So you input the single photon states here, and you go through the phase shifter. The phi is the phase shifter, shifting the phase of the single photon states to phi. And this one here is the polarized beam splitter. We call this PBS. That polarizes the single photon states into either the plus or minus state or the right-hand and left-handed state, the H and V, and split those photons into like different paths. So if you like use this interferometer and estimate the outcome probabilities in a in the single photon basis, then measuring that photon in that and then measuring the photon in M. The M is a bit string from 000 to 111. So if in these situations, the input single photon state, you have inputted two single photons, you also have to measure the two single photon outcomes. So that will be a possibility of 6C over 2, which is 15 possibilities if there is no photon losses. So M is that kind of output, and that probability is given as this figure on the left. It is so the probability of measuring a single photon state in an M-bit string is given as the permutation of a matrix given by the matrix represented by this interferometer in the middle that represents the phase and the polarized beam splitting. So the permutation is quite similar to the determinant, but not quite, because actually computing determinant of exponentially large, even for exponentially large matrices, we can compute the determinants in a polynomial time. Polynomial in the size of matrices. However, for permutations, we have to compute exponentially many different permutations of the products of each matrix. So if you think about determinants, computing determinant is basically computing the different sequences of the elements of a matrix in a sequential order. Like, for example, for 3 by 3 matrices, you have to compute 8 different components. I'm sorry, six different components. That's n factorial. However, for matrices for determinants, there exists efficient algorithms that can compute those values, but not for permanents. So computing the output probability is exponentially hard. That's what exponentially hard for classical computer senses. Obviously, it is very simple for quantum computers because you just have to measure the outcomes, and that will be basically it. For Gaussian boson samplings, it's quite similar, but a little different from normal boson sampling, is that you input a squeezed vacuum state. I'll explain what and how to create squeezed vacuum states in later presentations. It's quite similar to single photon state, except for they have some squeezing parameters represented by R and S. So if you input the squeezed vacuum state and measure the outcomes on a photon number basis, then obtaining M photon number basis is basically similar to the permanent. We call this the Hefferfeld, just defined as this fellows here is quite similar to permanent. It's just also exponentially hard, unlike determinants. So in a key sense, even though we can create these matrices exponentially, experimentally. Actually, computing the real outcome is exponentially hard because computing the permanent and the hyperfile of a given matrix is exponentially hard. So that's where the computational complexity comes from. If you have any questions, you can just ask any questions in the meantime. You can interrupt me anytime. So please feel free to ask questions. And okay. The goal of the Gaussian boson sampling, I guess this figure is quite similar because it's also similar to random circuit sampling, is to generate the Haar random state. So this output state in a filter number basis has to converge to a photon, has to converge to the Haar random state as if this matrix is random enough, meaning large depths enough. So actually these Haar random states are different from classical random in a sense that there's no heavy outcome. So heavy outcome means output probabilities with large probabilities compared to the average one. So if you think of classical random states, then the all probability. So if there are two to the n possible outcomes for the classical random states from 0, 0, 0 to 1, 1, 1, then measuring a single outcome in a certain bit string would be a probability of 2 to the minus n because there's no reason to prefer any certain state from the other. That's different for Haar random state. If you use this mathematics and derive so on, the probability decreases exponentially. So meaning that there is a certain bit strings that have more probabilities to be measured compared to the other ones, and those although exponentially small still exist. So that's where we come as heavy outcome generated because there's bit strings that are more frequently measured. So that's how you can distinguish between the states I generated is rather classical or quantum because you cannot verify it explicitly since you don't know the outcome. Since you cannot compute the exact outcome, that's also meaning you don't know the answer because you cannot compute it classically. You can only do it with quantum computers. And in the meantime, you cannot compute the probabilities with quantum computers. For you have to compute probability, you have to perform state tomography, which is exponentially hard. That's also for quantum computers. So there's no way you can know the answer. How you can verify is to check whether you have a heavy outcome generated by measuring the probability, by measuring a few probabilities, not all. So if you are certain you have heavy outcome generated, that means it comes from a Haar random generator, unlike classical generator. So quantum computers only output bit strings. And there's nothing you can do only with the random bit strings because everything can create random bit strings. Like even monkey can create random bit strings. If you give bananas, then it will give 1. If you don't need bananas, then it's 0, then it's a random bit string. How would you distinguish a random bit string created by monkeys with a random bit string created by a quantum computer if you don't know the exact answer? There's a problem of verification in quantum sampling problems, and one way to verify is to check whether you have heavy outcome generated. So actually that was performed in this experiment, which I will explicitly present on the later presentations. So I will skip these details. Actually, you have seen this many times, I guess, from now. It's just that there's a complexity theory. The evidence is that it is exponentially hard. So yeah, if you have questions, you can come back. But I guess not everyone had listened to my first presentation, I guess, so I'll just quickly go through the reviews. So it just basically means that quantum sampling problems, even approximating it with an exponentially small multiplicative error given as this approximate C gap P problem. Gap P is a quantum sampling problem. It's harder than approximating a sharp P problem up to the same multiplicative error small c. And sharp P problems are much harder than NP problems. So it basically means that sampling problem is very hard if polynomial hierarchy does not collapse, meaning P is not equal to NP here. The polynomial hierarchy is a sequence of NP oracles. So sigma 1 is NP, sigma 2 is a NP problem if you have an NP oracle. It means that if you can solve NP problems, if you have a like magic, some kind of magic that can solve NP problems efficiently, then NP over NP or sigma 2 is a class of NP problems, assuming you have an NP oracle, you have access to the NP oracle, which obviously you don't, it is purely theoretical. However, what's basically known as is that even if you have infinite series of NP oracles as you go to the infinite polynomial hierarchy, that entire infinite hierarchy is still contained in this P sharp P problem. So it means having a sharp P oracle is much stronger than having infinite NP oracles. However, if you only have access to the approximate sharp P oracles, meaning only if you can only solve sharp P problems in approximate order, then the power of the oracle is much more confined, less than the third level of the polynomial hierarchy. This is proven by the Stockmeyer's algorithm here. I will not go into what Stockmeyer algorithm is. You just only have to know that there exists a mathematical proof that the approximate Sharpe oracle is confined in the third level of polynomial hierarchy. But even approximating, so if you have the ability to solve sampling problems approximately, then those computational powers are basically equivalent to the Sharpe oracle, which is much larger than the polynomial hierarchy. So these inequalities all serves basically proving that approximating Sharpe problems are easier than quantum sampling problems, and basically concludes that sharp sampling must be very hard. And if you can do it, then it would be very, very efficient. Meaning, if you can perform sampling with quantum computers, then it means that you have a very high computational power to perform steps. So what's exactly hard to achieve if you have a sampling problem is there's several more steps to compute. That's hard to compute. However, I will focus on two steps: the total variational distances and the heavy outcome generation. So total variation distance, also given as TVD, is like absolute distance between the exact distribution. The p-axis is the exact distribution of computing the bit string x. X is a bit string, and psi is obviously a quantum state. So the total variation distance is a distance between these two distributions, the exact and the quasi distributions. Actually, I neglect 1/2 here. I forgot. I apologize, but basically it's given as these values. And what's proven by this PLR paper is that achieving exponentially small, like order of 2 to the minus n total variation distance TVD is still gappy hard. So that's quite, I guess, counterintuitive because you have 2 to the n outputs. Achieving even 2 to the minus n total variational distance is still exponentially hard. It's like quite interesting. Another thing is I have interest before is the HOG, the heavy outcome generation, which is the number of bit strings x1 over xk with more than 1/2 fraction greater than the median. Median is like, I guess, about log 2 of the average value. So median is in a hard random state, log 2 times 2 to the minus n, because average is 2 to the minus n. So heavy outcome generation obviously basically means that there's more than 1/2 fraction that is larger than the median. So that's the theoretical background of Gaussian Boson samplings. If you're more interested, you can ask questions anytime, but at the time being, I'll skip to the next part, to the exponential implementation. So how can you perform Gaussian Boson sampling? So this is the actual layouts in the science paper I've introduced before. They first created squid state with this kind of the architectural layouts. They lock the phase of the squid states and they insert to this like beam splitters. So you insert to this interferometer here by the screen square and you measure the single photons and you measure the outcomes in a single photon number basis. So that's the very general layout. I'm not sure how they actually perform this kind of like large experiments. For Seoul National University students, you take intermediate physics lab 1 course and where you have a single photon interferometer experiment. That was kind of awful for even for we have only like one interferometer. No, not even yeah, maybe one interferometer because we have like I'm not sure, maybe. However, in this like experiment, you have like hundreds or even thousands of these polarized beam splitters and phase shifters. You have to measure them all in the photon number basis. It's just like I'm not going to do this experiment, even though even if I'm going to be an experimentalist in the future, you should not do this. Like basically, you have to use all of your PhD time, and that will not be even enough. And I'm a theorist, so I'm not going to do this experiment. I'll just only explain how they did it. So, as I said before, they first created the tumor squid states, also abbreviated as TMSS. It also abbreviated as two-mode squid's vacuum state, so it's same as TMSV. So they're basically both are same. What they mean is that they first use this pulse laser split it by the beam splitter. So you shoot in lasers, go to the beam splitter. So you only use the half of the beam splitter because this unpolarized laser is transferred to half to each other. And when you like insert to the beam splitter, you focus this split beam into what's called PPKPT, the periodically pooled potassium tinted phosphate. So what basically it does is it tune uh, the phase of the entire pulse laser into us, so it follows the Gaussian distribution. So this blue curve, I'm not sure if you can see this blue curve, but this blue curve represents the Gauss error function, also given as ELF. That's given as the so ELF is given when you exponentiate the e to the minus x squared, which is a Gaussian distribution. So obviously it starts from 0 to 1 because it is an exponential of probability distribution. So if you integrate all, then it has to go to 1. So what basically this sub does is that it matches the phase of the entire pulsed laser inserted as given as crystal length. So crystal length in the center, that's where the phase is all locked. So you can see that there are most of the lasers are like have their phases locked in the middle because that's where the slope is the smallest. That goes if you go back to the like edges, like all to the left and all to the right, then you can see that the distribution of phase drops exponentially because the entire PDF follows the Gauss error function. So after passing through the PPKPT, it generates a squeeze state, which is given as uh, uh, phase given as the Gaussian distribution. So actually in this state, they have used 25 different PPKPTs. So this B represents the Fourier function of these 20 different PPKPTs. So I'm not sure if you can see in this figure, but these two figures listed this eta and I'm not sorry, R and phi matrix phi which basically represents how much the inputted single photon state is like squeezed. So this TMSS state is given as this velocity. It has exponential phase differences for the given input state 0, 0, and represented by this R and phi. So this all parameters represent the R and phi of a squid state. So they have total in 25 tumor squid states. So after creating these tumor squid states by passing through the PPKPT, they have used dichroic mirrors to like split them and also use KTP crystals. KTP just stands for this potassium tinted phosphate here to like, I guess, have a time walk with, so to compensate for different polarizations between different time walks, meaning like just different mirrors and different optical paths. So that's how they created tumor squid states using like this kind of layouts. So if you like measure the correlations between the two different Vannier functions, then they're like just all uniform, meaning that there's no correlations. It's just like distributed at the same the wavelength peak with no preferred directions, no specific preferred directions, and these are the I guess the fidelities, the purities, and the efficientness of these 25 generated states. So you can say that the fidelity is like on average about 0.95, which is like very high, I guess, for the time. So this is how you create the tumor squid state, the TMSs. So this is from the supplemented figures. So if you import the 775 nanometer lasers, you split them in the polarized beam splitters. There, I guess, in total, 13 of this polarized beam splitter for the first time. So if you count all of this, PPKPT is 25. So they're in total 13 paths and 25 tube modes. So you split them in polarized beam splitter, you go through the PPKPT, you go through the dichroic mirrors, then also to the KTP, also, and you can all send it to the couplers to couple it laterwards. So this is the exponential layout of generating TMSs. So after you create a TMSs, you have to check whether it is a single photon state, because actually creating single photons, even for now, which is about 5 years from this paper, is still, I guess, quite hard. So you have to check, always check whether you have created a single photon state by that, and that can be achieved by measuring second order correlation functions defined. Actually, this is not the definition. This is how it's given if you compare it for the two different TMSs. So if you check the second order correlation function of TMSs, it's given as this value here. But however, what we can have to check is that we can actually estimate the purity by this given PMSs, because this large P is a purity above given state where N is the primary mode of a TMSs, and this M tilde is a primary mode, and this M tilde is the secondary mode of a generated TMSs. So at time 0, the second order correlation function is given as follows. At time t, it decays something like this. So by fixing a purity, we can actually compute not only the exact 2-point second order correlation functions, but also the visiting probability measurement is given as small p here. So actually there's 2 parameters, but you can check 3 different physical quantities. So if you know 2 of them, then we can basically know another one. And that's given as this figure. So at fixed purity, P equals like 95%. This is how the 2-point correlation function decays. So actually, we can see that this, if as the probability increases, or measuring probability increases, then we can see that basically the second order correlation function decays. And obviously, since this TMSS, there's a phase factor phi here. You have to like lock the phases. So this figure represents how to lock phases. You first input the generated TMSS mode into some kind of this A and B mirrors. I'm not sure how to call them, but what basically they did is that they split this single TMSS state into 25 different ones by using, I guess, optical path differences. And in the process, they carefully design these two interferometers such that the phase between all 25 different TMSs is all like stabilized. So actually this figure represents the 5 radian given as an hour, so you can say it's pretty much stabilized. If it goes like to like 60 minutes, it's still quite stabilized, like fluctuating, on average on 0 radian, and their standard deviation is like less than 0.1, which is, I guess, is quite good for at the time being. So they have to basically lock the phase to really estimate the effects of a polarized beam splitting and phase shifters after in the interferometers. So the interferometer, because actually to like be classically hard, you have to generate high quantum entanglements. So you have to basically couple the two different TMSS modes after you lock their phases. So this is the given actual matrices of how they given. Actually, two most grid state, there's two photons there, so you can split those two photons each into a different single photon states. So that's what they first did. They first input the states given here, and you go to this triangular piece given as this B, and a rectangular piece given as this A figure. Then you can split the single TMSs into two different single state photons. So since there are 25 of them, then the total photons will be getting it to 50 by n 50. So in this 100 by 100 matrices here, what basically they did is that they first shift the two different photons into H bases and V bases. During the process, you mixed up their entire configurations. So you first generate entanglements by creating entanglements between the same bases in the H and V bases respectively. After you do that, you create H inputs and V inputs. You also entangle them by, I'm not sure how they did with these modes, but what they basically did is that they entangle different H and V base spaces. After they first create entanglements inside the same basis. So that's how they fully created the hard random matrices by using the interferometers. So these are the explicit matrices of their interferometers, and this matrix will be used to like create hard random states. So after you create hard random states, how would you measure the probability? Because you can only measure the as I so-called the bit string number basis. So if you have a click count C1 to C100 and threshold to detect a non-zero photon is given as this follows here, it basically means that detecting non-zero is just subtracting the entire probability of measuring of the zero photon state, which is n bar plus 1. I'm sorry, 1 over n bar plus 1, where n bar is the mean photon number. And you can compute, actually you can compute the amplitude if you know the click counts by this given matrices. So you can compute the amplitudes of 100 possible outcomes. I'm sorry, 100 by 100, because this matrix is 100 by 100. So if you measure if you measure the matrices with this method, what basically gives, if you compute the U dagger, it should be identity because it is a unitary matrices, and what basically they observed is actually it is identity. So you can choose that all diagonal is 1, and the imaginary part is like quite close to 0. And this is they plotted the histogram of the amplitude distribution, and as they achieve quite similarity with theoretical Paratomas distribution as they should if they created the true hard random states. So what they did is that they first compute the amplitudes, and they also track the phases. So you can see that phase is still quite long after going through the interferometers, and this amplitude distribution quite resembles the exact theoretical Hall random distributions with overlaps of, I guess, up to 80%, so meaning that this region is the 80% of the entire distribution. So they have checked that it is a quite good Hall random states. Okay, so I apologize for this kind of disconnection. The internet situation in Chicago is actually, at least for residents, it's not great. So I'll resume. I guess we have checked until this part, correct? I guess I opted to do slides 10. I'll start with slides 11. So after generating output states, you have to measure the physical quantities. Actually, this is the number of photon. Click number is the number of photons. And what we can see that is even if you like perform several like thousands, like close to millions of more than millions of outcomes. If you measure it more than 80 millions of times, then most of them are still concentrated in the middle level, given as the Gaussian distribution. And the mean photon number is like a little more than 40, even though you input 100 states. So that's actually quite, it means that the photon loss rates are like more than 50% at the time being. And I believe it is still not that high even 5 years later. So actually, photon loss is a critical problem in the Gaussian boson sampling experiments. So if you measure the TBD, the total variational distance, which I proved that said that it is proven to be hard to achieve exponentially large numbers. Well, basically they achieve is like a little close to 0.1, which is quite small, but not exponentially small. So this is the like state of the art that you can achieve in terms of TBD in the 2020s. So actually, these states represent how much this sparse state is like high dimensional because we have used 100 filters. This is like 2 to the 100, 2 to the 100, which is like a little more than 10 to the 30. So it's quite complex. If you compute the probabilities by this given filter number, the output click number, it basically fits well with the experimental states are quite different from distinguishable single mode states. So it's different from single mode states and it's also different from thermal state, which means classically random states. So you can check that these bit strings are not classically generated. They're generated by quantum samplers, not classical samplers, or not even monkeys. So this is how they distinguish between their outcomes and then verify that their outcomes are generated by quantum samplers, not by something else. They also checked the two-point correlations and discovered that their experimental values coincides well with theoretical curves given that it's red and orange ones, unlike the thermal state distributions or the single mode squeeze state distributions. And they achieve quite high heavy outcome generation rates for boson samplers. They achieve HOG more than 1.0 when the photon losses are not quite even large. On the contrary, with thermal samplers where the heavy outcome generation rates are like very low, like near zero. And they also check the 40 different outcome combinations and prove that their probability distributions are like more packed, more compact in the region where the probabilities are higher. So meaning it also basically proves the heavy outcome generation that their states that they generated are actually satisfy the heavy outcome generation conditions given as the theoretical curve here. So this is how they verify that their quantum sampler machines are actually not classical, but quantum, even though you have photon losses, about nearly 60% photon losses. I will discuss some kind of limitations of this paper. As a theorist, I'm studying quantum information theory, and as a theorist, you can measure other quantities such as cross-scientific benchmark or the collision probability. We have to compute them to like verify whether it is a classical random state or Hall random state. Actually, you can do it with Gaussian boson samplers, and I guess paper from Sanado and computed it. However, in their paper, I guess for some kind of technical reasons, they don't, which is, I guess, like, so if you measure more and more physical quantities and compare them with theoretical values, then basically you can cross-verify whether we have really performed quantum sampling machines. So actually that will be the first limitations or first caveats of this experiment. Another experiment actually published quite recently by Professor Chang-Hun Oh, I guess in Nature Physics in 2024 with Professor Liang Jiang and Professor Zhong at Seoul National University. Actually, Yang Zhang is at University of Chicago. I'm actually working with him. And what they basically did is that they constructed the matrix product state to like basically reproduce this by quantum sampling machines by creating an MPS and performing direct sampling with I guess computing conditional probability. So what they basically did is they created the answers of this density matrix given by the partial trace of A, which is given as in this fellow. So if you like perform time evolutions with this matrices, then it's given as this fellow. We can actually represent the kth power, so the kth moment of the density matrices by just performing k different tensor products. And what we basically see is that the singular values after you perform the k distribution. So k is the number of I guess, outcome photons. So it's like in the order of tens for these experiments. What they basically see is that the singular values decreases exponentially as you increase as you increase the modes. So what basically means that we can efficiently estimate these entire density matrices if we just kept a few larger singular values because all of the rest decays exponentially, so it will be negligible in the long term. So this singular value exponential like decaying part is really a key of this entire paper. What basically this means that these states are efficiently simulable classically if the loss state is like quite high. So epsilon is the loss rate. So Professor Chang computed the upper bounds of the error losses epsilon r, and they get the upper bound given as this exponential minus 1/3 c squared LR, where L is the number of truncated photons. So with fidelity loss epsilon. So it means that we can truncate the entire n quantum states with this up to like L number of photons up to fidelity fidelity loss epsilon with where the L is like proportional to the inverse of logarithm. So if the epsilons are like fixed and if the photon loss and if the photon loss rates are like quite high as in this experiment, so basically it means that it is still classically computable. What it also means that if epsilon goes to zero, meaning no loss, if you retrieve if I'm sorry, if you achieve fault tolerance, that basically means that there's no way we can simulate efficiently with matrix product states or maybe other tensor networks because basically by then the singular values will not decay exponentially, so the error rates will be quite small means we have to use a large number of truncated photons to represent in the MPS spaces. So it means classical interactability. So so I will move on to conclusion. So Gaussian boson states same sampling is important for studying quantum advantage because quantum sampling problem is hard. And quantum random is different from classical random. That's actually the point of Gaussian boson sampling. And USTC have first performed GBS and published in 2020, but we are still uncertain whether we have truly achieved quantum advantage because for lossy Gaussian boson samplings, we can still reproduce the data, still sample the bit strings with tensor networks. So thank you for listening to my seminar. I'm very sorry there's a disconnection in my term. I will apologize. I will make sure it will never happen again. So thank you for listening to my presentation. If you have questions, please feel free to like ask or upload it on chats.